When we build a regression model, we want to know, is it a good model? And what we mean by that is, if I use the model with my observations, does it appear that the model is working? That is the model a good model? Does my data fit well in terms of that model? Now, I started this series talking about how the preference, if you're going to be scientific about this, is to create a theoretical model, and then once you have that theoretical model, test it. What we've been doing is more of an exploratory analysis where we actually built the model based upon how well the data were fitting with the model. So we are sort of urging a good model fit as opposed to testing the fit of a theoretical model. And if I were to switch to another data set, even taken from the same population, I might end up with another model if my primary goal is to try to find something that fits well with the data. And that's sort of the tail wagging the dog. I'm letting the data dictate the model. So I'm not a big fan of that, even though that seems to be what we're doing here, primarily because if you understand exploratory analysis and building regression models this way, then you can certainly build a regression model in which, rather than looking for the variables that provide the most fit, you actually look for the variables that fit in with your theory and then see how well the model fits. So either way you go, you're going to assess model fit at some point. The strength of the model depends on how well it performs with the observations, and we've already talked about the coefficient of determination. The coefficient of determination tells us the proportion of variation in the response variable that can be accounted for or explained by, or potentially even caused by, variation in the explanatory variables. The higher the coefficient of determination, that is, the closer we get to 1, then the stronger the model. But in addition to that number, that coefficient of determination that we calculate, we know that that is going to vary from data set to data set. That is, there's sampling variability associated with that. So how stable is this model going to be if we were going to look at it across various data sets? You well know from your first statistics course that if you calculate there to be a correlation among two values, that in fact that correlation will change if you take another data set, and you know that you can put a confidence interval on that correlation, which implies that just because I observe this correlation with this data, it could be anywhere between this lower value and this higher value. Anywhere in between there is what I actually expect the population value to be like. So the fact that we have a coefficient of determination in our particular data set, let's go ahead and remember what that was. I'm looking over here in the console. I see that multiple r squared of about 0.27. So even though I have a 0.27 here, do I know that I can actually infer that this model is going to provide reasonable fit in the population? Because this is a sample model. It is not the population. It's an estimate of the population model. So that's what this topic of model fit is all about. So we already know the coefficient of determination, but the F distribution is what we use to see if we can make inferences. Is the model stable enough to infer fit? Now, the F distribution is likely to be new to you. Some of you may know about it, depending upon previous statistics. But if you're learning about multiple regression for the first time, it may be the first time you've encountered the F distribution. So I'm going to do two things. One is I'm going to give you a little bit of information about the F distribution right now, but I'm also going to post a few older videos that I made that go into much more detail, and you will find them right down at the bottom of this playlist. I'm going to tell you about mean squares in more detail and then the F distribution, because as you'll see, We have to have mean squares in order to have an F distribution. So let's talk about that now. Let's talk about mean squares. Mean squares are estimates of variance. And the general formula for a mean square is that you take the sums of squares and divide it by the degrees of freedom. Well, think about that a moment. Think about when you were learning your very first statistics and you learned about the mean and variance, or the mean and standard deviation. How did you calculate that variance or that standard deviation? I believe that what you did is you took the deviations from the mean, you squared those, you added those all up, and as you know, we've now called that the total sums of squares. And then you divide it by something like n minus 1, which you later learned n minus 1 is just degrees of freedom. So the sum of squares divided by the degrees of freedom, that's the exact same thing when you very first learned about variance. And then, of course, if you wanted the standard deviation, you took the square root. But we're going to be sticking with variance here. So we're looking at mean squares as the sum of squares divided by degrees of freedom. And note, we have multiple sums of squares, don't we? We can partition that total sums of squares into a part that's due to the model and into a part that is unexplained or residual. That would give us two mean squares here, one for the model and one for the residual. Well, what do we want? What we want is for that model sums of squares to be as big as possible, as close to the total as we can get. Because remember, the model sums of squares represents how much of the variation that you're accounting for by the model. So for a really good model, you would like to have high sums of squares, and you'd like to have a small sums of squares error. So you would like sums of squares for the model, we want that to be large, and we want sums of squares that is unexplained to be small. Well, what about if we take the ratio of those? And that's what leads now, when we take the ratio of those, is what leads to our F statistic. An F statistic is the ratio of two independent estimates of variance. So in linear regression, the F statistic is going to take these two variances in a ratio. All right, now let's think for a moment about what we would expect the F statistic to be if our model was just nonsense, if we just pulled it out of the air, had nothing to do with theory, it had nothing to do with the data we were observing. It's just a worthless model. Would we expect that the mean square for the model, would we expect that to be 0? And the answer is no. We wouldn't expect it to be 0. Just like when you take two uncorrelated variables, have nothing to do with each other, and you take a set of data and you calculate a correlation, you don't get 0, you might get 0.02 or 0.03, maybe even 0.07. You get some value. And that's because of random fluctuation. So interestingly, it can be shown, I'm not going to do so here, but I invite you to watch the videos in which I go into more detail. Interestingly, it can be shown that the mean square for the model estimates random error when there's no value in the model. If the model's totally worthless, the mean square for the model isn't going to be 0. It's going to estimate the exact same thing that the mean square error estimates. Now, it does it in a different way. And so you're going to get two different estimates, but they should be close to each other. That is, your F statistic, your ratio of these should be close to, let's take and make this a close to instead of a, should be close to 1. Okay, that F statistic should be close to 1. And what happens when your model starts improving? When you get better and better and better models? When you get better and better models, then what's going to happen is your F statistic now is going to get greater than 1, and it's going to get bigger and bigger and bigger the more you have in your mean square for the model. So the F follows an F distribution, and an F distribution is a skewed distribution that starts at 0. The F follows an F distribution when the model is worthless. So therefore, if you think about how we make inferences, we can make inferences here about our model in the same way we make inferences about the mean or proportion or any other statistic. If we have a null hypothesis that says, I think there's nothing here, I think the difference in means is 0, I think the difference in proportions is 0, or in this case, I think the model is worthless. That is, our beta coefficients are all 0. And so the explanatory variables aren't contributing anything. If we think that, then we will have an F distribution, and therefore, when the model does provide some value, we won't have this same F distribution. We'll actually have values more out here. Actually, let me switch to a bigger page. So when the F distribution is, or when the null hypothesis that the model is worthless is true, then you get an F distribution. I don't like that picture. I'm going to draw it a little bit different. Okay. When that model of the F distribution, when the model's worthless, if you actually have then a model that is worthwhile, instead of looking like that F distribution, it's going to look more like this. That is, as you draw different samples, you're going to get Fs that are higher than you would when you draw from a F distribution with a worthless model. So what we do is we play the hypothesis game that we play. We strike a critical value, and we say if we end up seeing our F over here, which becomes much more likely as your model becomes worth something, if you find that you strike that over there, then what we're going to have is a larger part, and in this case I didn't draw that so much was over there, but let's say it became more even like this. Then we have a lot of our F values are over beyond the critical value. We reject the null hypothesis, and we conclude that the model is worth something, that there's a stability in our fit here. So that's how we do hypothesis testing. If I were to go back to my example here, now that we know about that, let's look up here in where we looked at the summary for our beds income model. Here's what we have. We have an F statistic here that is 9.167. And if you watch my video on mean squares and F statistics, you'll see that we have actually a numerator degrees of freedom and a denominator degrees of freedom for the F statistic. Remember that the F statistic is a ratio of two mean squares, each which have a degrees of freedom. So there's a degrees of freedom in the numerator and a degrees of freedom in the denominator. Those are the parameters of the F distribution, those two degrees of freedom, and two different degrees of freedom, not a degrees of freedom equal 2, but two different degrees of freedom. And from that F statistic of 9.167, we got a really tiny p-value. So looking at this again, if I was to draw the F distribution with those 2 and what was it here? 2 and 50 degrees of freedom. So if I was to draw that F distribution out there, and then by the time we get way out here, let me do it again. I'm not making my tails here small enough by the time we get way out here to 9.167. We have very, very tiny amounts of area beyond that. So that allows us to reject the null hypothesis and conclude that the model is making, in fact, a contribution, that there is stability to this model, that even if I were to do repeated sampling from the same population and get another sample and try out this model, I expect it to have some value. Note, I'm not doing a confidence interval here because we have two coefficients and I'm combining them. However, each of those two coefficients, we could create confidence intervals for each of those individually. So let me go ahead and scroll down here, and let's go ahead and enter in a code chunk. We're going to have to clean all this up a little bit later. And let me show you a couple more functions here that we could use. I'm going to put in 3 lines that I'm going to copy in. And we've called this the beds underscore, not dot, income model. Okay, let me go ahead and run these one at a time. So our first is a correlation between our observed, and which is the what we actually saw in terms of the number of physicians, and our predicted, what we predicted for the physicians. If I were to take that correlation that I just calculated there, it's 0.518, and square that, you see that I get the 0.2683 we get here. So the correlation coefficient, the multiple correlation coefficient, is simply the correlation between our observed and our predicted. Now, what's this next line do here? This next line gives us a nice little analysis of variance table where we see the sums of squares and the degrees of freedom for hospital beds. We see the sums of squares and the degrees of freedom for income. Now, the model degrees of freedom and sums of squares are these things combined. So in order to get the model sums of squares, I would actually be adding up the 6523 plus the 13502 to get 20025, and the degrees of freedom would be the 1 plus 1 for those coefficients. So I would have 20025 divided by 2, and that's my mean square for the model, is 10012.5, and here's my residual mean square down here. If I take 10012.5 divided by my residual mean square, I end up with that 9.167, and that should ring a bell. That's what we saw up here for the F statistic. It's the ratio of the mean square for the model. And you see the 2 degrees of freedom where they came from? 1 degree of freedom for each of our coefficients. You see where the 50 came from? We started with 53 observations. You subtract 1 degree of freedom for the grand mean, and that gives you 52. Subtract another 2 for the coefficients, and that gives you 50 degrees of freedom. And one more thing that we can look at here, and that is actual confidence intervals for both income and for hospital beds. No surprise that neither of these confidence intervals have 0 in them, because remember up here we found that the p-value was small for beds, 0.023, and was even smaller for income. Okay, so we need to kind of pull this all together and clean up this report a bit. So I will finish the primary topic in the next video and start working on cleaning up this report. But don't forget, after this video series, you can watch a couple of videos on mean squares and F statistics so that you can have a better understanding of these additional statistics.